how to predict the performance of a snap fit. So this is a topic that really kind of covers a lot of industries, and so what are we talking about when we talk about a snap fit? So it's a connector, and this connector it's gonna snap right into place, but is it going to break? If I use a plastic component here, am I going to damage it in some way? As I'm installing. So the motivation for doing an analysis up front to make sure that to meet the requirements and um, be able to withstand its operating conditions in service. So yeah, if we study this product performance virtually, we can lead to fewer prototypes, faster time to market, and fewer failures in the field. And so these are a couple of examples that I have here. Food container lids, toy assemblies, uh, buckle straps in luggage, and accessories for camping equipment and tie down straps, such as it may be. Electronics enclosures. So I got an enclosure example here, and two different types of snap fits are shown here. One is or these annular type of snaps, and then we also have cantilever type snaps shown in these other four examples. So um, those are probably the most common types of snaps that we see. We see these in 3D printed parts, plastic molding parts as cheaper alternatives to other types of fasteners like bolts and screws. And so, keeping with the STS theme of wearing out the E-rod, I've got an example where we created a hubcap um, in inserted into a wheel that was a new version of a wheel that Siemens created for the E-rod demonstration, and the whole digital thread that goes with that fantastic content and hardware. And our intent is to predict the performance of the snap fit assembly in the context of our hubcap. We're going to use Simcenter Nastran Solution 401. So we're looking at contact with large displacement, elastoplastic materials, and multi-step type of sequencing of our load. And so just some background here. The snap here, it's going to act um, as a fastener to keep components in place once assembled. So once the snap is installed, um, it's going to kind of keep things tight and just not really do much of anything until someone comes along and decides to disassemble um, the assembly. In terms of analysis, these snaps often exhibit symmetry. So we see an example here where I've got a luggage snap for straps where the you have two snaps, but really you can reduce this down to one snap for your analysis model, and we're going to have that in our case as well. Um, of um, results that you want to look at, do you have concerns about the material yielding while the snap is being inserted, or do you have concerns about the amount of force required to insert or retract the snap during assembly and disassembly processes? An accurate evaluation of the snap's performance, is going to provide insights into your design process. So that's really what we're going to be looking at, um, context of this presentation. So, from the EROD perspective, this is actually a new version of the wheel as part of our digital thread story, where we designed that wheel inside of NX and took it all the way through manufacturing. And if you go to one of these conferences where the EROD is showcased, you'll see the actual hardware in place. This hubcap as well. Um, and in terms of our analysis, we're going to measure the performance relative to uh, the yielding of this component. It's something that we don't want to have happen during the insertion of the hubcap into the wheel. And then we're also going to look at the load effort. So in terms of this is like a time history or load history of a graph of reaction force. So we want to evaluate the amount of force that's required to insert and retract um, that or the hubcap. And then in terms of key functionality that we're going to use, it's solution 401 multi-step nonlinear. Cyclic symmetry is going to be used. Contact, and then a nonlinear material as well. Look at this in terms of three phases. So the modeling of the analysis, the actual setup of the solution, and boundary conditions, and then look at the results at the end. So first, we take a look at the modeling. So how do we simplify the model and prepare the geometry for the analysis? And the one thing to note is that there are 5 snaps on this hubcap, so we can reduce this down to a 1/5 model and use cyclic symmetry. We also have this very detailed wheel, and we don't need the bulk of the wheel, so I can reduce the model down to just a chunk of the wheel. The stiffness of this portion of the wheel is still going to be a lot more stiffer than that snap. And then the key here is that we still retain the inner surfaces where the snap head is going to ride against the wheel's inner surface. And then we're using cyclic symmetry to produce a 1/5 sector of this geometry. And we also used some split body operations on the wheel and divide face operations to prepare the geometry for our contact meshing requirements. Yeah, we want to accurately depict the geometry as mesh in really the snap and the contact regions. So the snap, it's an extrudable kind of swept. It's a combination of swept and extrudable geometry. So the head is actually revolved, and so swept, I guess, is swept. But one is a revolve. So this portion, then it transitions into just an extrude up here, and but this is all easily meshed with brick elements. So that's the approach I took, using six rows of elements through the thickness of this cantilever here. We look at the wheel itself. You can see I've got maybe some refinement in the contact zones. So smaller element size around the the blend where the snap is going to come into contact with the wheel. Also, I've got refined length in the contact zone as the snap is going to traverse. But away from there, I can get away with much larger elements um, to completely define my sector. Yeah, and here we talk about the contact mesh um, intricacies, so to speak. So in the tangential direction, I've got the same number of elements spanning across the wheel as I do the snap. That's really done to improve our contact results, to get a matching mesh on both sides of the contact. And then the the cap of the hubcap is just tet meshed, and we use a transition with pyramids. And kind of already alluded to this, I've used mesh refinement on the curved faces. So had local mesh controls, um, controlling the mesh in the contact zone, and then use the option to project nodes to CAD to get an even more accurate depiction of the mesh relative to the curvature of the CAD as opposed to maybe the tessellation of the polygon geometry. In terms of the materials that we used in the model, the wheel was assigned a linear aluminum, and the hubcap, it was going to be, it's the intent is to print this with a steel, and we use that as a nonlinear material, as an elastoplastic type material with stress strain data, capturing its nonlinear behavior. And then next step would just get into the definition of the solution setup to include loads and boundary condition type of steps. And first key is the surface to surface contact. We're defining contact between the head of the snap and the inner wall of the wheel. That I had equal spacing through the revolve direction of the wheel and the head of the snap. That reduced the interference between kind of mesh-induced interference between the contact faces due to mesh discretization differences. So I wanted to keep that discretization the same. At a reduced element size in the contact area to better capture the curvature and a better depiction of those faces for contact. And then we see some additional parameters here, kind of grayed out on this slide, but we'll talk about that in subsequent slides, how those affected our analysis. Also, maybe want to mention, we use friction in this model of a value of 0.1. I really didn't have much thought into that value, other than something on the order of a metal contacting another metal. So whatever those typical friction values would be is a starting point. So I did play around with some contact parameters. So on the BCT PARM card of Nastran, I had 3 of these that I wanted to highlight. And the first one is being auto scale. And the challenge here was that during these solutions, sometimes the contact was chattering. It looks like it's going to start to converge, and then it takes a regression. Looks like it's going to converge and takes another step backwards. And it's clearly not going to converge, after say 25 steps. And then it's going to cut the time step and start all over. And then I was seeing this behavior quite often. And Well, this is kind of an indicator that your contact stiffness can be too high. When you're seeing chattering, um, it's a good bet that your contact stiffness is too high, and this auto scale will allow you to um, increase or decrease the uh, the contact stiffness. So you can also do this using normal and tangential penalty factors, um, or you can have Nastran massage those how it thinks it needs to have them massaged with auto scale. And with auto scale, you do give a a penalty factor scale factor. So Nastran is going to compute the contact stiffness as it does relative to the materials of the contacting parts, and then this will auto scale what Nastran is computing, as opposed to the user maybe saying, well, this is what the normal tangential type of penalty factors should be. We're going to scale what Nastran is computing. And in the case of this chattering, it's a good first recommendation is to reduce the stiffness by an order of magnitude. So the default for auto scale is 1. And in this model, I reduced auto scale to 0.1, and it did, give me some much improved results. I have a little bit more discussion on auto scale um, in a subsequent slide as well. The second contact parameter is, I guess it's the integration order, INTORD, and INTORD affects the basically the number of contact elements that are going to be defined in the model. And there's 3 values for INTORD. You have reduced, high, or reduced, increased, and high. And I always kind of mess this up when I think about it, but it's a low, medium, or high type of arrangement in terms of the number of contact elements that are going to be created. And this model was exhibiting some problems in the sense that um, the contact is very localized. It's really um, a not contact over a large surface area. These aren't planar surfaces. They actually have curvature in 2 directions. So curvature about the wheel's rotation axis, and then curvature about the blends as well. So um, it's really highlighting that contact is spanning across a narrow surface, or not even a surface, or it's just reducing down to an edge. And in that situation, you really want to use the highest option for INTORD. So setting INTORD to high provided much smoother contact results in my iterations in running these models. And then this last option, well, before I even talk about that last option, maybe I should highlight this animation and how it really shows the effect of this contact being really along a line or an edge across the this radial wall. So that's kind of what the previous option with INTORD. That's what that was improving the contact convergence due to that phenomenon. This G update is a geometry update of your contact elements. You would do this in large displacement situations. And I turned it on. I don't know if it was really needed to be turned on because my steps were large enough that maybe Nastran was automatically updating my contact anyway. But the intent here is make sure that you update the contact geometry as often as is needed. So in this case, I used G update and I forced it to update at every iteration. Um, that I didn't really pay attention to see if in this case if I turned G update off, if Natran was doing that for me anyway. But I just kind of said, I'm going to update at every iteration because I know I'm moving this uh, component, quite a bit during my analysis. Okay, so um, next we get into the loads and boundary conditions. The first boundary condition being that of um, cyclic symmetry. So we do have a 1/5 sector model for this, and we need to couple the surfaces on the cut plane. So I need to couple the wheels cut plane surfaces with respect to one another, and then the same thing for the hubcap. And it's just a reminder that you know this cyclic symmetry coupling enforces displacements on the dependent side. So say the yellow is being dependent, it'll force the displacements on that side to match the displacements on the independent side. Uh, and you don't have to have matching meshes. In this case, for the wheel, I did have matching meshes because I was revolving a swept mesh or a hex mesh through here, so I got matching meshes. But for the cap of the hubcap, this is a tet mesh, and I didn't enforce any um, surface dependencies here. I just generated a tet mesh, and then I coupled these two faces, and cyclic symmetry was able to handle that. Next, we get into the constraints. We talk have constraints on the base of the wheel just to fix it and keep it from moving rigidly. And then I've got constraints on the cap here where I'm fixing the radial and tangential directions. I actually, with the fact that I have cyclic symmetry, I could have just fixed this in the tangential direction and freed up the radial direction. Um, so that's an option for you as well when you're using cyclic symmetry. And the last bit of information needed was the actual axial and force displacement of the hubcap into the wheel. It's just a simple linear ramp over time where I'm inserting the hubcap and then eventually have to pull it back in the opposite direction to bring it back out. Okay, so next we're going to talk about some key loading conditions in the overall view of the assembly and then disassembly. So first, to point out here is that you don't have to run the full analysis in terms of insert and retraction to rule out a lot of really bad designs. If I look at just the insertion, and I can get some, you know, bad bad results in terms of the product performance. So I don't need to run the full use case. I can eliminate a lot just with a subset of my intent. So this was model one that I was running, where just inserting the hubcap until it meets that radial inner wall of constant radius. And then, conversely, also looked at the situation where, after I get some good designs, take a look at those in the context of retraction. And so now the way these two models differ is really just in the idealized part. So you know the starting point for this geometry was where the snap was just touching the wheel, to get the insertion started, and then I used the move face command in the idealized part to move all the faces of this the the hubcap solid body to the point where it's just touching at the point of when it's fully engaged, or fully inserted. So again, I can validate good designs to make sure that they pass both load cases. And then the final piece is um, to validate the piecewise solutions in the context of a full insertion and retraction. Yet again, the geometry is a bit different here. So in my idealized part, you'll see that this inner wall on the wheel is much smaller. So there's no point in me needlessly inserting this all the way across a um, constant size wall, along the axial direction. I can shorten that up, speed up my analysis time, and then get the insertion and the retraction in steps from this time point of view. And then, so this is really representing three analysis setups and three different, idealized part type configurations um, to get these done. Okay, so then we want to talk about nonlinear problems in general. Nonlinear problems are hard even when you just have a single type of nonlinearity. And here I wanted to study multiple types of nonlinearity. So it's best to start linear and layer your nonlinear complexities. And in this case, I started with a linear model and set up the contact, make sure that was giving me sensible results, and then on to adding the large displacement. From the large displacement, um, made it multi-step uh, in terms of inserting and retracting. So, and then the last addition to the nonlinearity was adding the material nonlinear capability. Okay, so then we get into a discussion of the results. So here we're going to be concerned about the yielding of the snap and then the insert and retraction forces. But in addition to that, we can look at the contact, and is the contact giving you sensible results that you would intuitively expect? And honestly, in some of the first models that I ran without some of those contact parameters, I ended up seeing a lot of concentration of the contact forces on the ends, and so not necessarily running all the way through the contact zone. And sometimes I was even seeing the contact forces on the snap being misaligned with respect to the wheel. So say, um, I almost thought it was like a timing sequencing issue where the the results were getting jumbled up in the OP2 file, but really what that in that case it was highlighting that my intward setting of using reduced or increased wasn't sufficient for this geometry, and I needed to go to an intward value of high. And so yeah, you want to always make sure that your contact forces are making sense. And then we can also look at total strain. Does your strain results indicate a potential for yielding and failure? So with respect to Simcenter Nastran, solution 401, and total strain, you get contributions from thermal strain, elastic strain, and plastic strain. And in this case, I don't have any material. I'm sorry, and any thermal loads. So I'm really looking at elastic strain and plastic strain. And in this animation, you can see when the snap gets inserted fully, the snap becomes totally unloaded, and yet I still have some non-zero strain values. So that's an indication of the yielding that's going on. I've got some plastic strain left over, and we can also break out the analysis of the or look at the results in terms of elastic strain, thermal strain, and plastic strain. And then we get into the topic of the insertion and extraction effort needed to assemble and disassemble the hubcap. And some of the key events here over time, we want to see a graph of that reaction force or that insertion force. And the way this was done was we were looking at the reaction force from the enforced displacement, and we did this with a result probe where it summed up the reaction forces in that axial direction. And then over time, I was able to graph that, and we see, we have a certain peak insertion effort. So this is when the snap is traveling over the blend of the wheel, and then we get to a peak point, and then it starts to settle down until a point where it meets that the wall, the constant inner radius wall of the wheel is this section here. And at some point, the wheel or the snap is going to engage the chamfer on the wheel, where it's eventually fully seated and unloaded. And at this point, you see, we went from a positive insertion force into the negative region. So that snap actually sucks into the wheel once it gets into the chamfer, and it's following the path of least resistance. So there's a chance that you could actually pinch your finger when you're inserting this into the wheel. And then this next stage is showing where it's fully loaded, and in my geometry, I didn't have contact of the surface of the hubcap hitting a surface, of the wheel on where it would mate on a planar face. So there was a time here where it's getting unloaded, or it has no load. The snap has no load, so this is a zero force region. And then we start pulling the snap back out in this direction. So you can look at this graph and you could say, okay, well, I can easily come up with some requirements in terms of effort. And I didn't have any requirements, but you can easily see that, maybe I would be concerned about the amount of effort required to get this the snap back out of the hubcap back out of the wheel, and how much force do I need to push the hubcap into the wheel. So then, yeah, if we intend to print it, Siemens isn't a manufacturer. We have a limited budget in terms of our marketing content. If we want to print it, we want to make sure that we want to not break it. It's going to install the first time, and so this is just an example of some of the design iterations that I went through in this process. And it almost looks like, Mark, you were just throwing darts on the wall situation. And it was at first, not being totally up to speed with respect to the maybe the problem I was trying to solve. But we're going to focus in on 3 of these this situation. And so each one we're concerned about yielding. We don't want to have any yielding going on when we insert this. And that this first design, it's I call it the angled cantilever. They're all cantilever, but I just have a single angle, so it's more like a straight cantilever. And this exhibits quite a bit of plastic strain, so 3 thousandths in terms of the strain, and it also has, when you look at this geometry, this is basically a lever arm. And if you can increase the lever arm, you basically are distributing the work and the effort across a longer distance. And when, in terms of the amount of work that a lever arm will do, for the same amount of force, if you increase the lever arm, you can get more work out of it. So that's the idea behind the introduction of these coils. So when I introduce these coils, I'm extending the lever arm so that the action is actually over a longer distance. And you see here, I actually, in this iteration, I reduced the plastic strain by a factor of 10. I went from 3 thousandths down to 4/10,000ths. But there's still some plastic strain down in this first coil. So I would really like to eliminate all the plastic strain. Um, I'm not really so concerned about the strain up here at the attachment point, because that would probably be addressed by the blend that would be around this attachment point in the actual manufacturing of the component. So then we go to our second coil design, which is our final design, and this gives us the longest lever arm in our three scenarios. And I completely eliminated the plastic strain in this model. So that is all good news, and we're heading in the right direction. So should we print this thing or not is the question. And before we answer that question, maybe we would want to look at our second design requirement, which is the insertion and extraction effort. And so we have our three designs as the matching the curves. So red is the red curve is the initial straight cantilever, and then the blue is the short coil, the green is the long coil. And you can see, keeping in mind this is the shortest lever arm and the longest lever arm. As we increase the lever arm distance using those coils, we actually reduce the amount of effort that we would be required in terms of insertion. I mean, the same thing happens on extraction. We reduce the amount of effort required to extract this by increasing the length of that lever arm. So yeah, we didn't really have a target for this, but a manufacturer could easily use this as a requirement. So we did end up going with that last design, and we printed it, and hopefully the results will show up in this video. So that was a video taken at the IMTS conference in Chicago this past September of last year. We printed multiple versions of these, so we got maybe like 5 or 6 of these that were printed up, and we're able to demonstrate that, at the booth, demonstrate the digital thread capabilities of the NX and Simcenter offerings. So, and the booth actually covered manufacturing and a lot more topics in terms of what we do at DAISW. So to conclude, what are the benefits of predicting the performance of snap fits using Simcenter? We've shown that Simcenter can address the needs of snap fit analyses. Simcenter 3D can reduce the time and effort by simplifying a 3D model to essentially the design features of interest. SimCenter and Astran can accurately capture the physics of the problem via multi-step loading, contact across large displacements, and nonlinear material behavior. And the results quickly ruled out inferior designs by way of a dedicated plastic strain result from Simcenter and Astran. And then we also were able to use a result probe defined on the solution in Simcenter 3D that allowed us to evaluate the effort required to assemble the hubcap into the wheel. The creation of the model and the interpretation of the results in Simcenter 3D helps the engineer better understand design implications and potential problems before actually having a product released. That concludes this presentation.